So today it's our pleasure to have Leon Glass as a speaker. Leon went to Erasmus Hall High School. Not only,
Is that right?
not only did you go there, he successfully graduated. For the record, this is the school that Bobby Fischer, supposedly someone who had an IQ of 180, flanked out. So Leon was educated as a chemist, and before he settled at McGill, he went through a stint of 3 postdoctoral appointments during which he studied machine learning, machine intelligence, theoretical biology, and physics. So for the past many years, he has been at McGill, and he has a chair position there. He is a Guggenheim Fellow. He's a Fellow for Royal Society of Canada, American Physical Society, and the Society for Industrial and Applied Mathematics. And it's our great pleasure to have Leon. He will talk about the relation, maybe complicated relation, between arts and science.
Okay, so thank you very much. And I thank all of the students especially for coming out when I'm sure there are more fun things that you guys could be doing or doing your homework or whatever. Can everybody hear me? Is the sound okay in the back? Yeah? It's okay? Okay, so I'm going to talk about how we appreciate what we see and what we hear. And to a certain extent, I would take the position that nobody really understands this. And certainly I don't understand it. So what I ask you to do as the audience in your own brains and minds is to try to be thinking about what you see, what you hear, and whether it sounds good or it looks good, and why that might be. Okay? So I'm not going to tell you very much about how much I know. It's more about how much I don't know. So in the talk, I'm going to give several demonstrations of sound generated in unusual ways, then several demonstrations of images generated in unusual ways, and then there are some basic questions. How do our brains interpret what we perceive, and what do we think is beautiful? I know this is a public lecture. Most of the people here look like they're associated with the university in one manner or another, but are there other people in here who are actually part of what you might call the public? Oh, terrific. So thanks so much for coming. Okay. So I'll start off by saying the ability to appreciate music and art are uniquely human characteristics. So one of the things that impresses me whenever I travel around someplace is almost every place you go, there are people who are involved with making music. There are people in bars or pubs or choruses or churches, and people are making music. So it's something very human. Art is a little bit more tricky, at least for me. I don't know. I think there are some demonstrations of monkeys doing drawings. So maybe if you live in New York City and you go to a gallery, you might be able to buy one of those drawings for some amount of money. So I don't know if it's uniquely human, but it certainly is a part of the human experience that cuts really across all cultures. I would say the pursuit of definitions of art and beauty arose in antiquity. I'm only going to give 2 examples. One is Aristotle, who said the chief forms of beauty are order and symmetry and definiteness, which the mathematical sciences demonstrate in a special degree. So I like that because people in my area are very interested in mathematics and symmetries and so forth. A contrary view is by a contemporary person who's interested in philosophy aesthetics, who says aesthetic theory is a logically vain attempt to define what cannot be defined, to state the necessary and sufficient properties of that which has no necessary and sufficient properties. Morris Weitz. Okay, so I'm going to start off talking about what I would call chaotic music and body music. And I don't know if I know that some of the older people in the audience have read this book book by James Gleick that came out in the 1980s, which really popularized some of the notions of chaos to the world. Probably most of the people here have seen Jurassic Park, the Jurassic Park 1, where Jeff Goldblum explains what chaos is. So when you go home, check on YouTube to hear Jeff Goldblum's explanation. It's pretty good. I'm not going to play it here. However, I will give you an example of chaos. And so this is oriented towards non-mathematicians. And one basic way to generate what's called chaotic dynamics is by applying an algorithm. The algorithm starts with a number, and it generates another number. Now, the concept of chaos is that I can have a definite rule, and when I apply that rule, I know a rule for generating numbers. I can find from one number, I can find the next number, but that rule generates a sequence which is random. It seems to be quite irregular. So we say take a typical number between 0 and 1. So people who are non-mathematicians would take a number, maybe a third or a fourth, but a mathematician might take 1 divided by the square root of 2 or 1 divided by pi. So a typical number between 0 and 1 has an infinite number of decimal places, which is never going to repeat. Subtract this number from 1, multiply the resulting number by 4 times the original number. This gives a new number between 0 and 1, and then you repeat that. Okay? So this is an example of what's called an iterative system. You start off with one value, you generate a new value, and then you use the same algorithm, the same rule, to continue computing new values and new values and new values. So for most numbers between 0 and 1, and this is most numbers, that means irrational numbers, numbers that can't be generated as a ratio between two integers, this will generate an aperiodic sequence of numbers between 0 and 1. And this is represented mathematically by an equation. If you don't know the equation, don't worry. The geometry of this is associated with very, very simple functions. And the lower right-hand corner here shows what gives a graphical representation of exactly that procedure that we just went to. If you take the values, so on the x-axis here, we have the values between 0 and 1, and the y-axis we have the values between 0 and 1. Given one value on the x-axis, we generate the next value on the y-axis, or xn plus 1, and we keep on iterating that process. Now, if you see what the sequence is that you get from that, the sequence that you get can be very irregular and aperiodic, in fact. And it can be proven. Some of the mathematical properties of this can be proven. Now, in one of my postdocs, I was at the University of Rochester. One of the people at the University of Rochester was named Jeff Pressing. Jeff Pressing was in the chemistry department. We were both working with a physicist named Elliot Montreux, who some of the physicists here will have met. Some of the older physicists may have known or met. And Jeff was a musician as well as a chemist. Eventually, he decided to go into music rather than to chemistry. And he also tragically died at a very young age. When he learned about chaotic music, when he learned about chaos, he generated time sequences which are generated by simple iterative systems, just like the one that I showed you. So I'm going to just play you, if it works. It does.
Example 1.
That's Jeff's voice. This tape goes on for about 30 minutes. Would you like to listen to more of it? How many people actually thought it sounded cool? Anybody?
Sounded like jazz.
Sounded like jazz. Okay, so some people kind of liked it. When I asked the same question in Montreal in my classes, they say no. So you guys are more avant-garde here. Okay, so might you say the following about it? I do not see how the feelings transmitted by this work could unite people not specially trained to submit themselves to its complex hypnotism, but I am unable to imagine to myself a crowd of normal people who could understand anything of this long, confused, and artificial production except short snatches that are lost in a sea of what is incomprehensible. Okay, so that's not a quote about Jeff Pressing's tape. What's it? Who is it and what is he talking about? Anybody know? No, not John Cage? Anybody? Another guess? One more guess? This is Leo Tolstoy describing Beethoven's Ninth Symphony. Here is other critical commentary. Oh, Pearl Erdos, one of the great number theorists, says, why are numbers beautiful? It's like asking, why is Beethoven's Ninth Symphony beautiful? If you don't see why, someone can't tell you. I know numbers are beautiful. If they aren't beautiful, nothing is. Okay? So here's someone not contemporary of Beethoven, but saying, oh, well, everybody now knows Beethoven's Ninth Symphony is beautiful. Here's another cut. So I live in Montreal, so excuse my French accent. Voici un étrange spectacle d'une barbarie laborieuse et puérile que le public des Champs-Élysées accueillait sans respect. Okay? What's that referring to? What? No. Music. Yeah. No. Music. French. No. Yeah. What? No. It's the Rite of Spring. Stravinsky's Rite of Spring. Okay, so in the Rite of Spring, which I think is a fantastic piece of music, in Le Figaro in 1913, this is what it was received when this played. It was also a ballet with people dancing around in leotards or whatever. So, but people got up, they booed, they screamed, they left the theater. Okay. Here's a series of pieces of a scientist musician, Diana Dabby, and what she did is she started with Bach's Prelude in C, and then she did variations of this based on some algorithm, based on some chaotic mathematics. So I'm just going to play. There are three there's one original. And she's a accomplished pianist. So this is her playing. Okay, so that's the original, and now she's playing variations. Raise your hand when you hear a wrong note. See, it still sounds like Bach, but it's a little funkier than Bach. It's okay. Okay. Okay, and there's one more, just more extreme variations. Okay, so you get the idea of that. So it's all based on the Bach. It's not original, but it's using chaotic mathematics to come up with variations on Bach's masterpiece. Now, this is a picture of the Grateful Dead, who I have to admit, when people in my generation were out there smoking and listening to the Grateful Dead, I was doing science. So. Say more about the Grateful Dead in a second. In McGill, there was a student named Mark Ballora, who's now a professor at Penn State. And Mark had a joint PhD thesis between the physiology department and the music department, in which he did what's called sonification of physiological signals. So the sonification of physiological signals, he took records of the heartbeat, and then he developed ways to sonify it. And I'll just play you data. So this gives huge compression of data. There are a variety of different techniques that he developed to do the sonification. This is a healthy heartbeat. Okay. And this is someone who has sleep apnea. In the middle of their sleep, they So if you're a doctor, so one of our ideas was this might be used diagnostically. If you're a doctor, you might listen to what's happening over the course of the night in a minute, and you can just hear what's happening, the way we use sound cues for many different things. So Mark went to the University of Pennsylvania, and in the University of Pennsylvania now, he started being interested in sonification of other things besides the heart. So he hooked up with a neurologist. He did two things. One is he hooked up with George Smoot, who's a Nobel Prize winner in physics, and they did sonifications of signals from galactic signals. And the other thing that he did is he worked with Mickey Hart. Now, Mickey Hart was the drummer for the Grateful Dead. Okay? Did anybody know Mickey Hart's name before this? Nobody? Mickey Hart was the drummer for the Grateful Dead, and we'll try to go to this first clip, and we'll try to play this. So this is multimedia.
What we're going to do now is I'm going to show you the rhythms of Mickey's brain superimposed on his brain in real time. That's our goal. All right, let's try this out. So let's show you alpha rhythms.
Adam Ghazali is a neurologist.
What you're looking at is real-time alpha rhythms. These are those first rhythms described by Hans Berger in the early 1900s. In Mickey's brains, changing in real time, recorded from this cap, superimposed on his brain.
This is very reassuring.
They are there. He has a functioning brain.
Oh, good.
It's
Above ground, that's good.
Now what I'm doing is showing you theta rhythms. Theta rhythms, you can see they have a very strong frontal dominance. These are the rhythms that are associated with attention, concentration, working memory, holding information on mind. We can view all these rhythms in real time. Right now, it's a demonstration. It's the first of its kind that I know of in experiencing this in a live audience here. But what we hope is that this will also drive the very research. Can being able to visualize your own brain rhythms in real time help you to control them? Okay, we have the rhythms going now. Now what we want to do is something also unique. We're going to let you hear the rhythms of Mickey's brain. So let's turn off theta, can we hear alpha? So what we've done is we've sonified the alpha rhythm. We've converted it from a frequency that you can hear into a level you can hear. That would be alpha. Let's move over, turn it off, and take a look at theta. Slower rhythm, deeper sound. So we kept the relationship between the rhythms. Theta rhythm is 4 hertz, so we just brought it up to a level you could hear, but its relationship with alpha is still the same.
That's Mark
How
in
about
the
gamma
background.
rhythms? Gamma rhythms are much more rapid. We're now displaying it as a high frequency. So let's bring on these rhythms and let's turn on all of the sonification of Mickey's brain and all the visualizations of the rhythm. So there we go. The song of Mickey's brain in real time with his visualization.
I give you my brain. Well, the sound of my brain anyway. Now, can you imagine being able to entrain with these rhythms, to be able to focus on a certain part of the brain, to be able to see what part of the brain lights up?
Okay. Anybody who wants to hear that more can go to the website. But they also, what Mark said is the video is from a presentation at the American Association for Retired Professionals, all of whom have heard of the Grateful Dead. The sounds weren't direct reflections of Mickey's brains. The graphics software was doing a spectral analysis and sending intensity values for the various regions, alpha, beta, gamma, etc., to my computer, where I was running oscillators that were transpositions of these frequency ranges, and their intensity changes reflected the intensity changes I was being sent. So Mark Ballora has collaborated with Mickey Hart on generating a few albums. This is Superorganism is one of them. Another is Mysterium Tremendulum. So there are a few albums in which they've done ordifications, not composed by Bach or Jeff Pressing, but which are ordifications of what's happening inside people's bodies or inside the universe. So these are also different ways to make sounds. Okay, so I'm going to, let's see, I'm going to stop the sound demonstrations here at the moment, and I'm now going to move over and say something about vision. Okay? So I'm going to start off by giving a demonstration, and we'll see if we can get the demonstration to work. Oh, maybe it should go on both screens. Okay. So when I was a postdoctoral fellow at the University of Edinburgh in Scotland, the person who I was working with, who was Christopher Long at Higgins, took a trip to Syracuse University in New York, talked to a physicist named Eric Harth, and Eric Harth showed him a demonstration which he thought was fascinating. He came back and he showed it to us, and I thought it was fascinating also. And the demonstration was, and unfortunately you cannot do this any longer, the demonstration was on Xerox machines. So the idea in the Xerox machine was to take a blank piece of paper, to stick it in the Xerox machine. This was really Xerox machines, none of the better technology machines that are made elsewhere now. Stick it in the Xerox machine, take an image of it, and then take that image and iterate it. Take an image of the image. So back in those days, first of all, the Xerox machines in Scotland, I hope there are no Scottish people here, were a little bit dirty. They had specks of dust. The paper was pretty crappy because the English people had cut down all of the Scottish forests. So the paper had little brown specks in it. And what would happen if you took the Xerox, and this is working, so that's amazing, you would get little black dots, okay? And then if you did the iteration of the iteration, so this is actually a copy from those days in 1968, believe it or not, okay? If you take the copy of the copy, then this is what you get. Okay, so you get more dots. And if you take the copy of the copy of the copy, you get more dots. And now you get more dots. Some of the dots, there were more dots, but some of them kind of wear off on the paper. Okay, these are transparencies of what we actually had. So you can keep on doing this. If you do it down to, let's say, here's the 12th copy. Oh, wait, so I'm only having a small part of the screen here. I would like to have a little more. Okay, so you get more and more dots, and I was very interested in this. So all of this was on paper. This was on paper, and I found it was fascinating, and I actually wanted to do an analysis of the spatial distribution of the dots. So the only way I could think of doing an analysis, oh, good, thank you, of the spatial distribution of the dots was to put the dots on transparencies, project them up on the screen, draw a bunch of circles like a bullseye pattern, put a single dot in the center, and then count the number of dots in rings around the center, and that could be used to determine, to compute what the spatial autocorrelation function was of these patterns of dots. And in the process of doing this, I made a transparency, and when I ended up superimposing one of the transparencies on one of the originals, for example, this is, I have a blind spot in my camera there. What's the, okay, so what do you see there? Nothing, okay? You just see more dots. Oh, it's from the light. Okay, that's okay. Okay, but in the process of doing that, I was fiddling around with the papers, and I ended up okay, so if I do this correctly, people say, oh. Whoops, so how do I get this? Well,
lamp.
okay, but people get the idea. Can you see that? Oh. Okay, so you can see that you can see this. So this is the 15th and the 17th copy superimposed. In fact, it's impossible to superimpose them both exactly, because back in those days, the Xerox machines had a slight difference in the magnification in the X direction and the Y direction. So they had slight changes in magnification. So they can't be done superimposed exactly. But you get the idea. You can see something, or I don't like to, if I give a talk, I don't like to tell people what they can see. But all of those who said, we're seeing something. And then there's an interesting question of how does the visual system, so what's the visual system doing here? This is a question which, in my opinion, nobody knows exactly how the visual system is seeing that. This is a very, very simple image. There is correlations in the image. For each dot, there's a second dot that's approximately around the circle centered at that point of rotation, which in this you can see right around over there. Okay? Now, when I learned something about this field called nonlinear dynamics, I realized that you could make other images than just circles. So let's see if I can get this to work. I may or may not be able to. Okay, so in order to get things done back in those days, which was the 1970s, we randomly plotted coordinates of 400 dots, and then we hired somebody to draft them. So this is 400 dots, and can you see, is there some, oh, the background is off, so that's, screw that up a little bit. It's not as compelling as the other images, but people can perhaps see a particular circular pattern there. If you, you can generate, let's see if I can get this. We can generate this one. So that's another transformation. Can people see something there? It looks kind of like what? Andromeda. It looks kind of like Andromeda. So this is just, you take one pattern and then you expand the other by 5%. And when I saw this, I was actually looking for a job, and I went to MIT. And I don't know if anybody here remembers John Deutsch, a physical chemist at MIT. Nobody heard of him? Yeah? I thought you were a member of the public. Well, okay. So, but John Deutsch is a physical chemist who actually later on became head of the Central Intelligence Agency in the United States. And I showed him this, and I said, this is my theory of Andromeda. It's a visual illusion. There's someplace a beam splitter in the universe, and it's rotating the image of the stars, and then you look both of them together, and you see the galaxies as a visual illusion. John said to me, Leon, if that's true, I guarantee you a tenured full professor position at MIT. Well, I'm a professor at McGill. So it wasn't true, but it was before people had discovered gravitational lenses and realized that the gravitational lenses could give rise to image splitting of images. So there's one other thing that we can show. If we do a different transformation, but let's just move on. This different transformation, we can also generate hyperbolas with this. So for people who teach mathematics, this is how I teach about geometry of critical points in differential equations or in maps. So this is essentially visualizing a vector field by plotting an initial point and then a slight point that's displaced by a little bit. Then our eyes are, in some sense or other, generating the image of the vector field. So we can generate all of the different geometries using these techniques. Okay, now we're going to try to go back to this. And this is a multimedia presentation, which is really dangerous to do. But so far it's working, and hopefully it will continue to work. Oh, wait a second. Oh, hold on. Okay, so I have to go back to my PowerPoint demonstration. Okay, so this is a picture of Benoit Mandelbrot, who coined the word fractals. He wrote 2 really wonderful books many years ago. And he said, fractals are geometric objects whose form is extremely irregular and or fragmented at all scales. Fractals are self-similar. A small portion, when enlarged, resembles the whole more or less. Fractal geometry occurs in nature, riverbeds, trees, blood vessels, et cetera, et cetera. So these are rather amazing images. And just as we could give a rule for generating that chaotic time series, you can given words, so you don't have to know mathematics, you can give words to generate the Mandelbrot set, these almost iconic images at the moment. So the way you do the rule is you take 4 numbers, you compute capital X is x squared minus y squared plus a, you compute capital Y, which is 2xy plus b. You go back to the start where you say little x is big X and little y is big Y, and you repeat this for some number of steps, for example, 256 steps. You determine the number of steps it takes until x squared plus y squared is greater than 2, and you associate a color for a point in the AB plane, with the number of steps it takes. The color is black if x squared plus y squared is less than 2 at the end of the process. The Mandelbrot set is the resulting image in the AB plane for initial point of x equals 0 and y equals 0. So it's a bit of a mouthful, but it's a rule which you can use for any value a and b. You can determine whether it's black or some color. And essentially, what it's doing is doing iterations of a map. And depending on the initial values, you either get a color or it's black and white. Now, now I'm going to go over here. And now I'm going to go to image, full screen. So this is what, whoops, I'm going to do it. I'm going to do that too. Okay? So this is what so if we could just go to lower lights here. I don't know if there's a way to make them a little dimmer. Okay, so this is a picture of the Mandelbrot set. So this is software. What I'm doing is I have software here, and the software is software which was downloaded a long time ago. It's from a company called AROS, A-R-O-S, and it's very nice software to generate this. Now, back in the old days, when I would give demonstrations of this, I would program a little HP computer, and it would take an hour to generate these images. Now, what we can do with this program is we can focus in at a very small region, and in that very small region, we can press the button, and it can go through the computation of what's happening in that region as quickly almost as you can press the gadget. There are some regions which I like more than others. We're just blowing up and looking at very small regions of this structure. So let's just do one more. So I'm just blowing up. Now we're at a tiny scale. This was done using 256 iterations. I can now go through 8,000 iterations at each point. I get that. I can change the coloring of this. Here's, what is this? Here's gray. I can do random colors. I can do rainbow colors. And I can change the color scale. So anybody who has a tendency for epilepsy, please close your eyes. Okay, so to me these are extraordinary images. It's generated from the application of a very simple iterative function. One can ask the question, and I ask the question, how come the sound that was generated by iteration of a very simple function sounded so crummy, and this looks so nice? This is my personal opinion of how this looks. So that's the demonstration of the Mandelbrot set. Okay, so now we'll see if we can get back to the presentation. And Okay, so we did the demos of the Mandelbrot set and patterns. Okay, so then there's a question of how do we see, how is our brain actually doing any of this processing? And this is from a textbook by Eric Kandel. Eric Kandel won a Nobel Prize in neurophysiology, and it's based on experimental work which was done by Hubel and Wiesel. These are two neurophysiologists who also won a Nobel Prize for this work. And the basic idea of what they said was that in the, can you see my arrow there? Okay, that there are cells in the visual system that appear to be hooked up to elongated receptive fields in the visual field. They respond to edges or lines, sometimes moving in one direction or another direction. Those cells seem to be hooked up to other cells. These simple cells appear to be hooked up to complex cells, which seem to have the inputs from several of these simple cells that are oriented in particular orientations in particular regions of the visual field. So when I discovered these dot patterns, my mentor, Christopher Longet-Higgins, said I should write up the results. So I wrote up the results that were published back in 1969. And I proposed that the visual columns in the cortex of cats, which had just been described, the functions of some of the cells, could be used to compute localized autocorrelation functions of the inputs to the cat's brain. As far as I know, this is similar to what people believe now. I refer to this paper. This is a paper that was published in Journal of Neurophysiology from the group of Movshan and colleagues, signals in macaques' striate cortical neurons that support the perception of glass patterns. So it turns out that those images of those dots are named for me. Okay, so those are now called glass patterns in the literature, and there are several hundred papers where people have manipulated various parameters of those to try to determine characteristics which enable us to see them. And this is one of the papers which tries to define receptive fields, tries to plot them out, tries to see if everything is working. Okay. So I'm not going to say very much about the neurophysiology of the brain. It's not particularly my field. However, there's a great deal of work done which is associated with trying to map out regions of the brain, how these regions are connected to one another. And there are some really absolutely stunning new techniques which people are using to be able to study the anatomy and also to study the functional anatomy of the pathways in the human brain. It's almost certain to me that the anatomy of the brain is absolutely critical to the functions that it does. And this anatomy is very complicated. One of the things that people are doing is they're trying to measure what people know as functional MRI. They're trying to see which areas of the brain are more or less active. These slides are slides that come from Matt Smith, and Movshan. This is unpublished. I'm not sure why they were never able to publish this, but these are patterns which are from macaque brain while it is viewing some of these dot patterns in different sorts of images. So it is possible to do recording of not direct recording of neural activity in the brain at the moment, but recording something that depends on neural activity of the brain in animals as they are doing various tasks. This is also being done in human brains as they are given pleasant or unpleasant tasks. This is from a group in Montreal, Zatori and Alan Evans' group. And then there are other work which is trying to see which regions of the brain might be more active or less active depending on the inputs that are going into the brain. This is with inputs that come from auditory cues. So why might we find the fractal images something which may be pleasing and the chaotic sounds not as pleasing? And one of the reasons is that we're actually very familiar with fractal images because, as Mandelbrot was describing, these complicated self-similar geometries are very much part of what's part of the world. So this is an image of the lung vasculature, and the lung is also solving a problem. Mammalian lung is solving a problem. How can we get unoxygenated blood, oxygenated blood, and air all put together in exactly the same place or very close together? And the way nature has solved this is coming up with this multi-fractionated geometry, this vasculature and windpipe geometry of the lung. In art, there's also images of natural images. This is from Elliot Porter, the nature photographer. And there are many elements in which trees and clouds and mountains all have some kind of fractal geometry. Jackson Pollock, there was a Scientific American article in December 2002 that tried to determine some of the fractal geometry that may be associated in Jackson Pollock paintings. There are scientists, Peitgen and Richter, who wrote a book, The Beauty of Fractals. Another book, Discovering a New Aesthetic of Art, Science, and Nature, Fractals, The Patterns of Chaos, by John Briggs. Two fine mathematicians, Michael Field and Martin Golubitzky, have a book, Symmetry and Chaos, A Search for Pattern in Mathematics, Art, and Nature. And here's a chaotic quilt. All of these are coming from simple iterative systems which generate these patterns of unexpected subtlety and beauty when put in the hands of mathematicians who have a highly refined aesthetic sense in art as well as in mathematics. So I think I'd just like to finish over here. So if we could go back to the last clip on YouTube. This is Mickey Hart. He's wearing goggles from Oculus Rift. This is a new immersive goggles. Lord knows what's happening in this video, but it's new ways of generating sound and light images. Interacting with the waves from his brain, fed into computer programs. Okay, so I will let Mickey Hart have the last word here, right, because this is a quote that I love. He says, "I believe music can play a crucial role in helping us transcend the divisiveness of politics, race, geography, and gender." This is particularly relevant given the current political situation in the world. That's my ad lib there. It is an energy that unites. It is also an energy that can heal. All we need is a groove to move our feet and a song to make the spirit soar. So thanks very much for your attention.
Thank you so very much, Leon. Now I would like to open the floor for questions.
I was going to, I thought you brought up a really interesting question when you asked why is it that chemicals don't make good music. And I think there might be something about self-similarity that's required and sort of repetition that you need to have. And I was wondering if you might want to speak a little bit more on
Sure.
that.
So there are a variety of composers, and I don't know all of that work, but there are a variety of composers that are specifically trying to embed repetitive themes, perhaps going at different tempos in compositions. I would also say that one of the aspects of chaotic dynamics is that there is, when you start to come close to an unstable manifold, as people were talking to me about today, you have repeating some of the same elements. In compositions, in classical music, you have theme and variations. You have reiterations of themes. So there are certain aspects in music which have iterative aspects. You also have to say that in the chaotic excerpts that we played, there was no musical nuance at all. Everything was played at the same amplitude. There was no changes of phrasing. There was none of the things that musicians want to put in when they're playing music. There was also an unfamiliar tonal structure because it wasn't according to the scales that we're familiar with. So there are many reasons why that would not be familiar to anybody and would be very hard to appreciate in the same way.
Other questions?
So touching more on that, when we discuss what exactly the brain finds beautiful about music and why we don't find the fractal music is beautiful, is there something throughout music, between cultures, throughout time, that is consistent, that we can see as, okay, well, maybe that would be a good place to look for what we find beautiful in music?
So actually this was my last slide, which I thought I should just finish where I was instead of doing this. I think that appreciation of music, art, and beauty depend on the cultures and what is experienced and how this past modifies an individual's brain. So I think that people's brains are very much shaped by their background and experience. And I don't know necessarily what the common motif is in all of the music. And the fact that many of the compositions that we now think of as being fantastic, great compositions were alien when they were initially presented is an indication. I think that our brains, I think, must have some regions, which was also part of the MRI studies, which light up when you like something. But what makes those things light up are probably conditioned by culture and background and experience. But these are questions that I don't know anything about.
So one of the big differences between music and pictures is that music is experienced over time. Has anybody explored using Markov chains to take one piece of music and transform it chaotically in that way?
I think the thing that comes closest to that is what Diana Dabby was doing, where she was doing some chaotic transformations of the music. But people may have done things, but I'm not aware of it.
I think that's a quite important point because I've ever did such an experiment, try to play music backwards in time. So the music becomes unintelligible or just similar to that chaotic music.
Okay, when I try to play Beethoven backwards in time, it sounds like Beethoven. So the chord structure still sounds like Beethoven, even if it's played backwards in time. So I'm not sure I've had the same experience as you have.
I can almost begin to have the illusion that I understand something about generating an algorithm and taking that and creating art.
have the illusion that I think I understand. When I look at Jackson Pollock, I'm looking at stuff that looks kind of wild and beautiful and interesting, but it's also splattered paint.
Yep.
And you're making sense out of the world that way. To me, they're opposite kinds of things. One is generated from a mathematical formula, the other one seems random. Is this a two-way street? What do we learn from the random stuff? What's the relationship between a calculated thing and a random thing? I'm not sure I get that.
So I don't get it either. And in fact, I don't actually get Jackson Pollock particularly. It may be great art. I'm not sure how we find out whether it's great art. But I actually like the way the fractal images look more than I like the way Jackson Pollock's paintings look. So I'm just not sure what determines the aesthetic. I can't give a good answer.
Could this perhaps relate back to the culture, art, and experience mentioned earlier? For example, when Jackson Pollock's painting first came out, people didn't really understand it, but now we live in a culture where people readily love and accept the thing. Now, all of a sudden, it's 10 times better. Like what happened with Beethoven's Ninth Symphony. Is the brain perhaps an iterative system in this sense?
A what system?
Iterative system.
Is the brain an iterative system? So once again, I'm beyond my depth in knowing what it is. For sure, the brain is a dynamical system. So those of us in the audience who are interested in dynamics can think of the brain as dynamics. Is it doing strict iterations the way the Xerox machine is doing iterations? I don't think it is doing iterations like that. I think it's running in continuous time, but I think that there are physical mechanisms, there's connectivity that we can understand a lot better, and I don't think we've scratched the surface.
Hello, Professor. Do you know much about Google Deep Dream?
No.
Oh, okay. They use a really cool algorithm and can reproduce and affect like images, not just images, but a lot of other things in a very dynamic and fractal-like manner sometimes, similar to fractals, I guess. So I was wondering,
but the input is what? What's the input?
So the algorithm trains on a bunch of pictures and learns commonalities in the pictures or images, and then it can apply these effects on other pictures as well. So what happens is that the other images can have a very strange effect that it looks similar, parts of it look similar to the images that it was trained on. So it's an effect that can be applied to video as well, and basically causes a fractal-like distortion on it. So it works on it. So I was wondering if you had, does your research into how the brain imagines and fractal images seemed pretty familiar.
Oh, so somebody just showed me a picture. Is this, I don't know if this is deep brain, but so I think that one of the things which is interesting in the current society now is that the technology for generating images, the technology for analyzing data, the technology for recording data from your body is totally entering into a new stratosphere which has been impossible before. And I think that it has profound implications for our understanding of how the body works, for how the brain works, possibly implications for medicine. We talked about that a little bit this afternoon. So to the students here, you're kind of on the threshold of really amazing new technologies which are able to transduce what's happening in the body, to transform them in ways which would really be unimaginable 10 years ago. So I don't know what, I should look up what Google Deep Brain is. Thanks.
I'd like to sort of throw out a little suggestion just to see if this stimulates some ideas. Obviously, when you create a chaotic result from an algorithm, there's order hidden in that chaos because the algorithm itself is a piece of order. So the algorithm sort of determines the chaos that's created. And so I'm wondering if one way to get better sounding music is to look for those types of algorithms that sort of apply themselves to the way music is created. You know, most music is created by a set of vibrating strings or vocal cords or mechanisms like that. And you can sort of look at the structure of these chords and look for algorithms that sort of match up to that type of thing. And talking about Pollock as well, I think Jackson Pollock, when he's throwing his random material out there, is actually influencing the randomness with his own brain, because our brains are looking for order and randomness. That's why we see people's expressions in rocks and burnt toast and things like that, is because we're trying to take randomness and make order out of it. And so I suspect that Pollock, when he's throwing all those random pieces out there on his canvas, his brain is also realizing what looks good to him, and he's seeing patterns. His own brain is influencing it. So his paintings really aren't as random as they may seem.
Yeah, so I think it's a very interesting and good comment. Thank you for that.
Right. I don't see any more questions, so if that's it, then let's thank Leon once again for being here.